Okay, so we did pretty well here. I'm going to take these a little further. And he probably did because I didn't really specify the form that I wanted these in. Just to apply the rules. That's a good start. So let's say we got x squared y cubed to the fourth. Well, exponentiation distributes over multiplication. This means x squared y cubed times x squared y cubed times x squared y cubed times x squared y cubed, which you could write as x squared times x squared times x squared times x squared, and y cubed times y cubed times y cubed times y cubed, which you could write as x times x times x times x, dot, 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 right? You're going to end up with 8x's multiplied together, and that's going to give you x to the eighth. Now, once you understand why the rule works so that you can always check yourself and make sure everything makes sense, it's a really easy rule to apply as long as you don't try to apply it with a plus sign in here. That's a whole different animal, okay? As long as you got a multiplication or division in here, you're safe using the rule. So that's going to be x to the eighth times y to the 12th. I could write out an extra step, x squared to the fourth, y cubed to the fourth. Okay, but everybody got that, so I'm going to kind of leave that one. Okay, this one. Okay, let's say we've got x to the fourth, y to the negative seventh squared. There's that. Well, applying the rule, that's x to the fourth squared times y to the negative seventh squared, which equals x to the eighth, y to the negative 14th. Okay, now sometimes you're asked to write without denominators. Sometimes you're asked to write these without negative exponents, right? So if that's to be written without denominators, that's exactly the way you want it. If you were asked to write it without negative exponents, then you would want to write this as x to the eighth over y to the 14th. Either of these is a correct answer as long as you haven't been told to either put it in this form or this form. You should be able to put it in either form. So everybody should be pretty good on that because everybody's pretty good with the rules. Okay, just in case though, make sure that's written small and abbreviated. It says no denominators. And this says no negative exponents. Okay. Okay. Well, on this one, we write like x to the fourth over y to the seventh to the negative second power. Well, that's going to be x to the fourth to negative seventh over y to the seventh to the negative second. That's that seventh when I wrote that down. I wrote it down right. Okay. And that's x to the eighth, x to the negative eighth over y to the negative 14th. Now that's kind of a weird form. It's got negative exponents and it's got denominators. You don't want to have both. Okay. So we write that down as, well, x to the negative eighth is 1 over x to the eighth. That didn't come out very well. So bad. It's and this should be over 1 divided by y to the 14th. Now that's a complex fraction. So you could write that as 1 over x to the eighth multiplied by y to the 14th over 1. Because you're dividing this by this, so you multiply by the reciprocal. This gives you y to the 14th divided by x to the 8th. Okay. You don't want negative exponent in your denominator. Okay, that's basically what you don't want. I said, you had negative exponents and you had denominators, you don't want that. Or you could have negative exponents. Yeah, you pretty much don't want negative exponents in denominators anyway. But the main thing you don't want is negative exponents in the denominator. Okay. Now this last one, you got, let's say x to the negative 11 divided by x times y to the negative 4. Well, how are you going to write that? Well, you have x to the negative 11, you have y to the negative 4. First thing is you can divide the x to the negative 11 by the x, right? And that's getting a little tricky. This is x to the negative 11. Divided by x times 1 over y to the negative 4. Well, that's x to the negative 11th over x to the 1. When you divide by power of x, you're going to multiply by the negative. It's like multiplying it by the negative power. So this could be x to the negative 11th minus 1, like you're subtracting powers, put that over 1, times 1 over y to the negative 4th, which is x to the negative 12 over 1. Not a room, don't want, can't not have room to write everything I want. 1 over y to the 4th is the same as y to the 4th. Okay. Now there's a rule says when you go from denominator to numerator, you change the sign of the exponent. It all comes from the arithmetic, what you do with complex fractions. So this could be x to the negative 12th, y to the 4th, or it could be y to the 4th over x to the 12th, depending on the form you want. I'm going to have to write this really small. I understand it very well. It could also be written y to the 4th over x to the 12th. Now, y'all seem to be on top of the exponents. It looks pretty good, but they can get a little tricky. So make sure you practice them and stay within the rules. But y'all seem to be in pretty good shape with these. Okay, to motivate scientific notation, we're going to count the number of grains of salt in this chunk of salt that I knew was there in my kitchen. It's been a couple of years since I used kosher salt for anything. It's way back in the corner, but I didn't have too much trouble finding it because there was one box way back in the corner that I couldn't identify. That had to be it. I looked up. Okay, so we try to estimate how many grains of salt are in this thing. Now, I really kind of want, yeah, there we go. Okay, we're going to get a good look at it. It's about the size of the end of one of my fingers. Smaller than the end of my thumb, probably bigger than the end of my finger there. It's about like this here. Okay, Now I'm going to make my estimate of how many grains are in here. Okay, I'm going to say there are 14,397 grains. It's about what you all thought, wasn't it? Okay. Now the board's back in focus. That's good. Now, how we're going to count these? Okay, well, I'm going to take this and break it up into a pile to start with. Okay, now we've taken the pile and cut it in what we think is about half. And hopefully this is okay. So we started out with a pile and then we divided, that was half of the original. Okay, then we divided that pile in half. So here's one half. And then the other half is all divided up. So then we took the second pile that was about equal to this one, and we divided it in half. Well, here's the half that we didn't subdivide, but then we had the rest of this constituted the other half. Then we divided this in half, which gave us this and the rest of this. Then we divided this in half and we got this. Then we divided the rest of this in half, we got this and these two. Now we think we can maybe count the number of grains in one or both of these two little piles. And from that, we can make a good estimate of how many grains we had originally. Now, one thing is when you divide it in half, you never get it right. So each person divided it in half. The next person took the bigger half and divided it. And then the next person took the smaller half after that division and divided it. And we alternated the bigger half and the smaller half, whatever you thought was the bigger and the smaller half. So I think we're going to get a pretty good estimate. Okay, so we did this. Are we in focus? I don't know. Probably not. A little hard to see. I've got some glare there. Anyhow, we took the smallest pile that was right here, it was divided. We had two little piles right here and here. And we moved those grains over here and then we counted. Okay. And got about 50 grains. So if there are 50 grains here, that means there are 50 here, which makes 100. Well, if this pile is equivalent to these two, there's another 100 there, that makes 200. And then this will be twice as big as whatever we had over here. That's 400, then 800, 1600, 3200, 6400. And if that was half of the original pile, as I came up with 6400 thinking, well, my estimate wasn't that bad. 6400 being off by a factor of 2. And then somebody reminded me, well, there's the other half. Okay, so this is a little more. We'll get 12,800, so that's about 1,500 short. So naturally, of course, I was the one counting. You don't know, I might have fudged. And, you know, I'm over there pointing at the board. And all I'm seeing is my feet and that board down there. Because I didn't bother to bring the camera. Oh, heck, now I zoomed it. That was a bad thing to do. Let's get the camera back up where it belongs. And we're going to zoom back just a little bit. So we get the whole board. Okay, so yeah, again, I said, well, I thought there were about this many. And that wasn't off by much. Now, you might consider that when we divided it in half, I don't think we really divided it in half. I think we probably divided it into about a third. Okay. So I think that my real estimate would be about triple the 6,400 that we got, which would be around 20,000. Still not a bad estimate. Now I've done this. I like to do this with my grandkids when they're about 8 or 9 years old. You know, when they learn to double things. And take a whole container full of finely ground pepper, pour it out, and start subdividing. Okay. A regular ground pepper, somewhere between 500,000 and 1,000,000 grains, gives us an idea of a fairly large number. 1,000,000's not all that much. Yeah, I went to a horse race last weekend. My daughter wanted to go to a horse race. We drove 250 miles to Lexington, watched a horse race, which is a lot cooler than I thought it was going to be. I mean, I love horse races. That's a horse race. The first race just, you know, kind of wiped me out. I love races. It reminds me of, you know, some of the competition I did earlier in my life, usually against weak competitions. Occasionally I won. Okay, but it just, you know, adrenaline rush on the first race. I thought I was going to pass. So exciting. Yeah, that by the 11th race, yeah, they're running again. You know, it wears off. Okay, the point is, it's a mile track. Actually, I think it was 9 furlongs, 1.125 miles. And it's just like the Kentucky Derby track. It's, you know, close to where the Kentucky Derby is, but it's, you know, a second tier track where you don't get the top horses, but the top horses at that track come out and sometimes do well in the really elite races. Those horses are amazing. Just looking at them, because it just happened. My wife had to go to the bathroom. We happened to come back just as they roped off the area when the horses came by. So we were right at the front row and saw them as far, and the musculature and the structure. I'm not an expert in horses, but I've seen a fair number of horses. Got a neighbor at a place out in the valley. He keeps some really nice horses. So I fed him over the. He used to ride a few, but never got to be a good rider. Didn't have the opportunity. If I had, I'd probably be dead now. Okay, that's all a digression, but the grandstands of this thing, you know, they run at least a quarter mile. Okay, it's a lot bigger than I thought it was when I saw pictures of it. So you can estimate how many people were there. Okay, but it wasn't that many because they have boxes and stuff, so that you don't get the density of people. The real dense part, I estimated about 4,000 or 5,000. So there are probably 6 or 7. Then there are a bunch of people standing. There's kind of standing room between the grandstand and the rail. Okay, they have 2 rails. They don't want you leaning over the real rail. So there's, you know, about that far between the rails. So there was a lot of people. It was hard to move. The people are nice, you know. They're polite. You have to be in a crowd like that, otherwise, I don't know what would happen. So, you know, wasn't that many, but maybe half that many people. You can estimate that sort of thing. If you've been to a big stadium or if you've been to a sold out race in Bristol, you know, you got 150,000 people, 10 times the number of grains of salt that we've estimated. Okay. So you get into big numbers pretty quick. Now, the whole reason I went through that, and excuse the digression about the races, but they're pretty neat. And the horse I thought looked best when they came by and won that first race. So I now consider myself an expert. There's one other, one other horse. Okay, the horses are, you know, taking them out there, escorting them out on the track. They have an escort horse. And they got it by the bridle. And most horses are just, you know, The one horse is just bobbing its head. It's every step, every time consistent. Okay. Now I already knew that horse was the favorite, but I said that horse just looks really focused and really composed. Well, he was a heavy favorite and he won by like 10 lengths. It was fun watching him. That all gets into the idea of the probabilities. You look at the tip sheet, and I don't gamble. I just don't get anything out of it except empty pockets. Okay. And it doesn't thrill me when I win because I know it's not to my credit. Okay. So, you know, winning a race, that kind of thrills me. I've won so few that it's a big thrill. Gambling, no. So, but I swear, I said to my grandson, who's about to graduate as an electrical engineer from Tech, said, we train an artificial intelligence to take the information just on this published sheet and beat the odds. And what do? You bet on a horse. You don't bet on the favorite because you don't get much return unless you think the favorite is absolutely going to win or has a very higher probability of winning than everybody else does. So it just all comes to probabilities and manipulating the numbers and so forth. And you get into some big numbers with that. There's a lot more, but because I was thinking mathematically about things when there wasn't a race going on. The race going on. Okay. All that comes down to, let's just take my first estimate, 14,000. 14,000 equals what? It's 14 times 1,000, isn't it? And of course, that could be written as 14 times 10 to the third power, because 10 to the third is 1,000. 10 times 10 is 100. Multiply that by 10, it's 1,000. That's 10 times 10 times 10. Okay. Now, 14 could be written as 1.4 times 10 multiplied by 10 to the third. Okay? That okay? Everybody understand that? Okay. And of course, 1.4 times 10 times 10 to the third is 1.4. Times 10 times 10 to the third, because you can group your multiplication any way you want to. And that's 1.4 times 10 to the fourth. Okay. This is called scientific notation. This number can't be less than 1, it can't be greater than 10. Okay. This is scientific notation. There are names for these. I'm not going to worry about the names. I don't think anybody uses them much anymore. Those names were important back when we had to do a lot of calculations using tables and logarithms before we had calculators and computers. Okay. Just after we stopped using sticks and marks in our cave walls. Okay. So there's our scientific notation. A number between 1 and 10, not less than 10, greater than or equal to 1. Okay. Here, book of math will tell you about all that. Just understand it for right now because it's not difficult. but we want to be sure we do understand it and understand why this is important. Okay. Now, I'm going to give you another project that I used in pre-calculus class the other day. Okay. You got a desert full of sand. You got a big pile of sand there. Okay. And you take a handful of sand. This is very fine sand, much finer than those salt granules. Okay. So you take a handful of fine sand and you dump it out on one of these tables and you count the grains. Now, how many handfuls or how many of these little blocks of salt could you hold in your hand? Don't say because we got the camera on. Let's discuss this. Okay, so we say somebody said, you know, I asked, could you hold 100? And people, I don't think so. Could you hold 10? Yeah, that'd be easy. So we split the difference sort of and say 50. And that's what somebody came up with. It's kind of what I was thinking. Okay. So, you know, any number 30 to 70, I think would have been a pretty good estimate. Okay, so let's say we've got a handful of coarse salt. About I use blocks. I should have used lumps because a block is probably more regular than a lump. So I wrote block and thought, okay, we'll use that. Okay, so how many grains of salt would there be? Now notice I've rounded this off to 14,000 because you know that 394 is not. You know, our estimate could be off by way more than that. So we'll just say 14,000 or 1.4 times 10 to the fourth. Okay. How would we multiply this? We multiply 50 by 1.4, wouldn't we? Well, that's 70 times 10 to the fourth, right? That's 7 times 10 times 10 to the fourth grains. Or 7 times 10 to the fifth grains. Okay. So that'd be 7 followed by 5 zeros because 10 to the fifth has 5 zeros. Okay. Now a million has 6 zeros. We went to 8 times 10 to the fifth, 9 times 10 to the fifth, then 10 times 10 to the fifth wouldn't be all that much bigger than 7 times 10 to the fifth, right? And 10 times 10 to the fifth is a million. So let's just say Now, grains of sand are way, way tinier than these grains of salt. There might be 20 or 30 million in the sand. Let's just say a million, because a million is a number that we can kind of almost grasp. Most people that keep a job for their lifetime with the current salaries, make at least $1 million over their working life. I mean, if you work 50 years, $20,000 a year, that'd be $1 million. And since there's inflation, you can expect that you would tend to make more than $1 million in a lifetime. Okay, so $1 million is kind of a number you can sort of grasp. Still hard to grasp. 1 million people. Well, fill Bristol Memorial Speedway 6 times. It's a lot of people. Okay, well, that's a big number. 1 million is a big number, but it's not all that big. Okay. So let's say that after counting those 1 million grains of sand, if you count 1 per second, that takes about a month. If you stop to sleep once in a while. Okay. Of course, they can have some feeding tube or something like that here. Just something you can get nourishment from without stopping your counting. Okay. And if you actually counted them all, now if you subdivide it, you could actually do it pretty quick in 10, 15 minutes. Take that grain of sand, divide it, keep dividing it until you got something you can count. Okay, well, but let's say you get those 1 million, okay? Then you got all the sand you need, okay? So let's just say that you develop a system where every grain of sand you count, you grab a handful of sand and dump it in the big container. 1 million handfuls of sand, okay? How many grains of sand you're going to have in that pile? What did the stupid camera do? Like the camera's on me rather than. I don't think I did that. Okay. Yeah, let's see here. Camera gets really good results, but it has a mind of its own sometimes. Okay. So anyhow, if you're watching this video, I don't know when the camera decided to lose its mind. That'll be easier to read now. Okay, so suppose we have It's not sand, this would be salt. What would go with salt rather than sand? Then we'll figure out what would happen if we had sand. Okay. How many grains do we have? Okay, so okay, so then we have a little discussion. And it comes down to we have 700,000 grains, or 7 times 10 to the 5th grains in one handful. And we're going to do 700,000 handfuls. So that would be 7 times 10 to the 5th grains per handful. That's 7 times 10 to the 5th times 7 times 10 to the 5th grains. Okay. Now, if you multiply 7 times 10 to the 5th by 7 times 10 to the 5th, that's your multiplication. 7 times 7 is 49. And what's 10 to the 5th times 10 to the 5th? 10 to what power? Show me with your hand. Well, 10 to the 5th, but you got 10 to the 5th times 10 to the 5th. What do you do when you have, yeah, 10 to the 10th? Yeah, you got it. 49 times 10 to the 10th. Well, that's 4.9 times 10 times 10 to the 10th, which is 4.9 times 10 to the 11th. Grains. Okay. Now, if you had twice that many, you'd have almost 10 to the 12th. Because 4.9 and 4.9 is 9.8, right? 9.8 times 10 to the 11th is almost 10 times 10 to the 11th, which would be 10 to the 12th. There's another name for 10 to the 12th. Everybody know what that number would be? Okay, so, you know, that turned out to be $500 billion. Okay. Now, how's $500 billion compared to the federal budget? It's in the tens of trillions. Okay, be about 1/20th of the federal budget. That's how many dollars? No, it's just what the economy generates. Okay, and you might agree with some parts of the way too, and some parts you might disagree with. Everybody's got their own opinions. But we're not going to get into the economics of it because you'd have to know way more than I do to say anything sensible. I don't know much economics. Now, one of you keeps looking at an economics book, so you know, probably know more than I do already. Okay, just learn to deal with the numbers should be good. Okay, anyhow, that's $500 billion. Now, that's if we are talking about grains of salt. If we're talking about grains of sand, they're way tinier than grains of salt. There might be 1,000 grains of sand for every grain of salt. Okay, fine sand. The way that salt is, that's pretty coarse salt. And if we have 1,000 times as many grains of sand, it'd be like 7 times 10 to the 8th. If I multiply 7 times 10 to the 8th times 7 times 10 to the 8th, I'm going to get 4.9 times 10 to the 17th. Okay. Now that's a number that's really pretty far beyond imagining. Okay. Although 10 to the 18th is like you line 1,000,000 grains up here, make a row of 1,000,000 grains. Then right next to that, you make another row of 1,000,000 grains and another one, and you do 1,000,000 of them. So now you got a layer of 1,000,000,000,000 grains. Now, 1,000,000 grains, you take all those grains, line them up, and do that 70 times. You'd have 1 million grains. And then line them up. That's it. Have a pretty big chunk. We easily put them on a football field. Wouldn't take a football field. Okay. Grains are pretty small. If they're a millimeter, well, it'd be more than a football field. It'd be like a kilometer by a kilometer. But they're small within a millimeter. So I'm saying a football field of grains. Then you do a stack 1 million high. So, you know, you'd be talking about the volume of a good sized skyscraper. Okay, or medium sized skyscraper. So that would have like 10 to the 18th grains. Okay. Now, number for trillion, after a quadrillion, you got a quadrillion, then you got a quintillion. Okay, those are big numbers, but you see that if we do this in scientific notation, it has advantages. First place, you don't have a string of 50 zeros running out there, or 7 zeros or 8 zeros. It gets clumsy talking about the zeros. We call these orders of magnitudes. Every time you go up a factor of 10, it's an order of magnitude. The number of atoms, particles in the known universe is estimated in the 10 to the 80th range. Okay? Because a typical galaxy, a large galaxy would have about that many stars. Now remember, you're on a beach with fine sand or on the Sahara Desert or someplace, you can scoop sand for a month and not make a big dent. There are a lot of grains of sand, okay? But what you can scoop in a month with your hand, working at it 12, 14 hours a day, 1 scoop a second. Give you about the number of stars in a big galaxy, about double the number. That'd be about 5 times the number of stars we think are in our own galaxy. Okay. Number of galaxies is about twice that number. We can talk about how many atoms there are. Okay. There are like 10 to the 23rd atoms in the end of my thumb. Okay. That's about 10,000 times of that 10 to the 18th. That skyscraper full of fine sand. So big numbers, you get them in finance, you know, we're talking pretty big numbers here. We're talking about 1 trillion, but when we're talking about the way matter is composed and the size of the universe and stuff, those numbers get incredibly huge. Okay. Scientific notation helps you get a handle on it. 10 to the 100th, incidentally, is called a Google. It was called a Google before Google was Google. Google named itself after a Google. Okay.